Hi, I'm Amir Hossein Mirza Bozorg, and in this video I want to talk about Comprehensive Abaqus Package Chapters 1 through 4, Getting Started with Abaqus Preview. How to ask your video-related questions. Don't hesitate to ask any questions you might have about the explanations presented in this video using the comments below. We try to answer all questions regarding the video details in the comments below. New Abaqus users who want to develop their modeling skills faster in their projects can request user-oriented online and offline services. Subsequently, we offer a step-by-step guidance, tutoring, and consultancy regarding their problems. The online service includes online sessions, and the offline service includes creating special tutorials. In addition, a combination of the two can be requested. Before watching the preview of each chapter, the table of content will be illustrated. This is the table of content for Chapter 1. Here we have a bar in Abaqus and then we mesh it. Okay? Converting the geometry into a specified number of finite elements. We call this meshing or discretization. Okay? We must do this in every analysis when we want to use a finite element method, okay? Because finite element solver works with mesh, okay? And you must discretize your geometry into finite elements, okay? As I define them. Do you have any question? Anybody? Is there any question? If you have any question until now, please ask. No question? Okay. And here we have an element. This is a hexahedral element. Okay. And here, as you can see, there are numbers on each corner. Okay. We have two kinds of numbers. Purple numbers and orange number. Okay, the orange number is element's global number. Okay, and these purple numbers are node's global number, and each node has a global number and a local number. Okay, local numbering is in the element. For example, 1 2 3 4 5 6 7 8. Okay, the local numbering starts from 1 to the total number of nodes. Okay, and this is the rule in all of the finite element softwares and in the finite element generally. And here we have three kinds of second order elements. C3D20, it is a 20 node quadratic brick, okay, or hexahedral, okay, hex or hexahedral. And this is C3D10, a 10 node quadratic tetrahedron or tetrahedral element. And this is C3D15, a 15 node quadratic triangular prism. Okay, actually we don't use wedge elements or prism elements too much. Usually we use hexahedral element or tetrahedral element. Okay, and here in the element type dialog box from the mesh module, you can set the geometric order, linear or quadratic. Okay, and here you can see the quadratic in the name of the elements. The elements order is indicated in its name. Okay, and here I want to mention several points. First point, all first order elements in Abaqus do not have a second order version. For example, there is no second order cubic element in the explicit solver element library, okay? And only a first order cubic element exists. But in the elements library of the standard solver, we have a lot of second order cubic elements, okay? Second point. One of the reasons for recommending the use of cubic and square elements is that even in the shape functions of the first order square elements, there are also nonlinear terms, which increases the accuracy of the solution compared to the case of using first order triangular and tetrahedral elements. Here, you can see the first order quadrilateral equation, okay? And here, as you can see, these terms are nonlinear, okay? But this is for the first order triangle. And as you can see, these are linear, okay? It is very good. It is recording. And as you can see, even first order quadrilateral element has nonlinear terms in its shape functions. Also, we have another thing, which is element formulation, okay? Element formulation, and these settings are related to element formulation, incompatible mode, reduced integration, and hybrid formulation. And later on, I will talk about these settings, especially in chapter 7. Okay, in the chapter 7, you will see the effect of using reduced integration, full integration, and incompatible mode. Okay, I will discuss it later. This is the table of content for chapter 2. Okay, now I start chapter 2. Chapter 2 is about consistent units, okay? Consistent units in Abaqus. I open Abaqus. I open Abaqus CAE. CAE means complete Abaqus environment, okay? But also we have another CAE, which means computer aided engineering, okay? This CAE does not mean computer aided engineering. It means complete Abaqus environment, okay? But let me tell you that this GUI or graphical user interface is not complete. Okay, it is not complete, and Abaqus has a lot of capabilities that are not included in the GUI. Okay, unfortunately they are not included in the GUI, and we must use coding and writing codes to use them, and also in this course I will talk about them. Okay, and here in all of the sessions of this course, we will focus on a standard solver and explicit solver. A standard solver and explicit solver are two structural solvers, and both of them are capable of solving nonlinear problems. Okay? Yes, it is recording. Very good. And here, suppose that I want to create a part. Okay? I click on create part. For example, its name is part 1, the modeling space is 3D, its type is deformable, its shape is solid, and I want to use extrusion technique to create it. And here you can see that approximate size is 200, but the unit is not mentioned. Okay, the unit is not mentioned. It is 200 meter? No. It is 200 millimeter? No. It is 200 centimeter? No. It is 200 micrometer? No. It is 200 nanometer? No. It is 200 kilometer? No. Actually, you must suppose the unit in your mind. Okay? In your mind, you set the unit of length to be meter. Okay? You select it. For example, I selected to be millimeter. Actually, it depends on the problem and several other things. Okay, we will discuss it. Here, I want to talk about this issue. Okay, selecting the system of units. Okay. I open chapter 2 slides. Now I want to derive the unit of density. Rho is equal to m divided by v. V is volume. Okay? So the unit of density is equal to unit of m divided by unit of volume. The unit of m is ton. The unit of volume is millimeter in the power of 3. So the unit of density is 10 to the power of 3 kilogram divided by 10 to the power of minus 3 meter in the power of 3. So the unit of density is equal to the 10 to the power of 12 kilogram per cubic of meter. Okay? This is very important. And I want to give you the first exercise. Suppose a micromechanical problem and derive the SI micrometer system of units. Select appropriate units for the primary variables and derive the units of secondary variables. Think about the effect of choosing the system of units on the simulation accuracy. For example, what is the effect of choosing SI millimeter instead of SI meter? Is there any difference in the accuracy of the simulation? Please think about this. Okay, tomorrow in the next session, at the start of the session, I will solve this exercise first, and then I will give you new explanations for other chapters. Okay, this is the rule of our class. At the start of each session, I will answer your questions about the previous session, and also I will solve the exercises. Okay, I will solve the exercises for the previous session. And actually here, for example, SI micrometer means that the unit of length is micrometer, and you can select the unit of force. For example, Newton or millinewton or micronewton. Time can be second, millisecond, microsecond. Okay, so we can have different combinations. Okay, we can have different SI micrometer system of units. Even for millimeter also, we can do like this. For example, if we use millinewton instead of Newton, the SI millimeter system of unit changes. Okay, but what I have told you for the SI millimeter is the standard form of SI millimeter, but also we have another forms. It depends on you and your simulation. Okay, and also this effect. Think about the effect of choosing the system of units on the simulation accuracy. Is there any question? This is the table of content for chapter 3. I want it to be job 1 and this is job 2. Okay, job 1, job 2. Now I want to compare Mises stresses. Here you can see their difference. Okay, and I set it to U2, U2. You can see the difference. Now I have a question. Please answer my question. Which one is correct? Job 2 or job 1? Which one is correct? Please tell me. Job 2, in job 2, the NLGM is set to on. Okay? In job 1, it is set to off. Okay? What is the difference? Which one is correct? I have only changed one setting. Everything is the same. Everything is the same, but you can see that the result has 20% difference. Excuse me, 12%. 12%. Here we have 12% difference. Okay, which one is correct? Please answer me.
Second one.
What? Job 1? Mariana says job 1.
Second one.
What?
Second one.
Second
NLGM.
one. NLGM is set. Okay. Rais says job 2 with NLGM on is correct, I think. Okay. What about the others? Sina, what is your opinion?
I'm not sure, but I think job 1.
Why?
I don't know, because the problem is not non-linear.
Okay. 1 centimeter displacement. Okay, it means that this is larger than the it actually it's beyond the linear domain. Okay, 1 centimeter for a 1 meter beam is beyond the linear domain. Okay, so the nonlinear assumption is correct. Another thing is that here, as you can see, the nonlinear deflection is less than the linear deflection. Why? Because when you set the NLGM is on, when you set the NLGM to on, more stiffness is applied to the system because of the change of the geometry. Okay, because it resists more to the deformation. Okay, because of this here the deflection is less. Okay, and is there any other question? If you have any question about this, please ask. Then I want to tell you about the tools of visualization module. Okay, I want to introduce them one by one. If you have any question about this discussion, please ask. And finally, this is the table of content for chapter 4. I create a copy from model 2. I name it model 2-1. It is not in the slides. Yes, it is not in the slides. And we have, yes, we have enough time. And then I go to the next chapter. In model 2-1, I use very small mesh. Small elements. I set it to ZY. I want to see what happens for the displacement. Okay, I increase it to 8. I increase it to 8. And also I increase it, I decrease it. Yes. And here we have a very small mesh. You can see the number of elements and compare it here. Eight times more. Job 2, 1. And this is a better problem. I mean, it is heavier. This simulation is heavier. And you will see that it takes more time. See? A little more time. You too. See? 8.88. 8.88. And if I open job 2, of chapter 1. Chapter 3, sorry, job 2. (8.82) viewport create tile vertically. Eight point, 8.88, 8.82, and now they are very close. Okay, now they are very close. And but see here, von Mises stress, if we here you can see that we have a very good resolution here for von Mises stress. Here also you can see neutral axis. This is something like neutral axis. Okay, this is not a pure bending, but it is close to pure bending. Okay, it is close to pure bending. So it is something close to neural axis. Okay, and you can see that here we have a better resolution of stress, and finally our displacement is close to the displacement of the beam, but this simulation is too much heavier than this simulation. Okay, and this simulation is very economical in comparison to this. Okay, I wanted to tell you this as Sina asked about it, so I saved this one. And what is the time? Okay, we have 10 minutes. I stop it. How to purchase packages or individual chapters. Each of the mentioned packages and individual chapters includes CAE, JNL, and IMP files, step-by-step tutorials with detailed explanations and investigation of the results, slides and reference papers and standards. Packages, specifications, and payment details are provided in the video description. Also, you can pay the cost of the mentioned packages in 2, 3, or 4 installments according to your budget or income. In the future, updates will be provided for free for everybody who purchases each chapter or each package. This will make the content up to date for new needs and new problems which must be solved via FE simulation. The cost of each chapter or package may increase after giving their updates. You can contact us using Telegram or WhatsApp, or you can send email to us. We have one-on-one tutoring on the AnyDesk, WhatsApp, and we can make special tutorials to your order. We can conduct high-quality simulations for your thesis, exercises, and industrial projects. Also, we offer support in writing the modeling and result discussion part of your thesis, and we have consulting services for MSc, PhD positions or job interviews, and also we can tell you how to prepare the presentation of your simulation works. Now I want to suggest you several related videos of our YouTube channel. Thank you so much for watching this video. Have a good time. Goodbye.